Hi, I'm Roland Larsson, and this is a video about the friction and the origin of friction. I will try to describe why friction occurs, and it's a two-part video, so let's begin. Well, the outline is as follows. We'll start describing some terminology, discussing some facts and definitions, and I will also bring up some classic friction laws. And then I will start discussing the origin of friction, and I will focus on two reasons to friction, and that is what we call the abrasive type of friction or plastic deformation type of friction and adhesive type of friction. And I will also, when I bring them up, those friction components up, I will also discuss how you can do to reduce abrasive and adhesive friction, or if you want to do the opposite, how to increase the friction. Sometimes you want to do that too, of course. Then you do it in the opposite way. So let's begin. First of all, as always, sit back and think yourself before watching the rest of the movie. You can start thinking about a typical example where friction is important, and then you can think about what is actually causing the friction in that case, and why is it so high or low or in some medium level in that case. So stop the video for a few minutes and think about that. Now I will start to say a few words here about what is true about friction. First of all, friction is not a material property. Remember that. It's a system response, it's not a material property. So that means that one surface cannot have a certain friction level. We may say that an ice surface is slippery, but it isn't slippery in some cases. So you must take into account both surfaces, properties, and the surrounding conditions on the operating conditions in order to say if this is a low, medium, or high friction case. So coming back to the ice spot, if the temperature is around 0 degrees Celsius, if you wear just ordinary shoes, this ice spot is very, very slippery for sure. But if you wear studded shoes, steel studs under your shoes, or if the temperature is -30, still wearing ordinary normal shoes, in both cases the ice spot is not slippery anymore. So it's always this two surface problem. Its friction is determined by both surfaces properties and conditions, and some of those are like hardness of the surface, how compatible the two materials are, the surface chemistry and physics of the surfaces, and if there are some fluids involved too, and if it's possible to form a lubricating film or not, if you have particles there. Coming back to the ice spot, for example, if you put sand on the ice, the friction is much higher, and that's the reason why you put sand on the ice, in order to increase the friction, of course. And also the surface roughness on both surfaces are important, could be important, not always important. What is true then is also that it's an energy dissipation process, so you always lose energy due to friction. So friction is a big problem in the world. It's something like 25% of the world's energy is lost in friction processes, and that's a pretty nasty thing, isn't it? So if we can reduce friction in general in the world, we can save a lot of energy, and then we can also reduce the carbon dioxide pollution of the atmosphere, of course. Friction is very difficult to predict. There are no mathematical models or physics models to be used to predict it accurately. And it's even difficult to measure it often. I mean, it's difficult to measure when you walk on the ice, for example. It's very difficult to measure what is the friction force there. So, before saying something more here about friction, we should think about some definitions about a few things. We should distinguish between friction force and friction coefficient. So the friction force is the actual force resisting the motion when you try to slide, for example, a box lying on the ground. You try to slide it along the ground. That's a friction force. But the friction coefficient is the friction force divided by the normal force, the applied normal force. But the friction force isn't mu multiplied by n, as you always see in many engineering problems, engineering examples. It's only when the box starts sliding, then the friction force is mu multiplied by n. You can take this example. You take your mobile phone, place it on the table in front of you, and put your finger in contact with the phone and apply a higher and higher force, and eventually the phone is starting to slide. But before you applied any force at all, the friction was zero, of course, because it didn't move, and that means that the friction force is smaller than mu multiplied by n before fully developed sliding occurs. So, and before that happens, even if you apply the force, the friction force is actually the same as the force you applied until then it starts sliding. Well, then it's also the same as the force you applied, because you must have force equilibrium, of course. A few words about these old guys, some name dropping here. You may recognize the names here. Da Vinci, Leonardo, the genius from Italy. He's nowadays said to be the first one studying friction and he discovered many of the friction laws that actually was rediscovered later than by Amonton and Coulomb. Amonton, he kind of rediscovered that what Da Vinci saw, that the friction force is proportional to the normal load and it's independent of the apparent area of contact. So this is an illustration from Da Vinci's work. So it doesn't matter if you place the box. This could be your mobile phone. If you place it in that way, or in that way, or in that way, or in that way, or in that way, and you pull them along the surface here, the friction force will be approximately the same in all cases. If now it depends also that it must be the same type of surface on all sides here, but it could be a box made of some wood or something. Approximately the same type of surface everywhere. So then it's independent of the apparent area or the nominal contact area. This is not perfectly true, but to start with, it's a kind of friction law that is useful in many ways. Coulomb said that also it doesn't matter how fast you are pulling those boxes along the ground. It's the same friction anyway. This is also not true, especially if you put some lubricant there. But those classic friction laws are useful in a way as a first approximation. The reason why the friction force doesn't change with load, for example, could be explained in this way. If you have if you have a surface with a number of asperities, we know from contact mechanics that that a surface, a typical surface, is only touching the other surface in a few contact spots like this. So if this is the initial condition with a little bit lower load, and then you increase the load, then you get more contact spots. But when you increase the load, each spot is growing. So this spot grew to this size now when you increase the load. But actually, the average size of the contact of the different contact spots remains constant. But on the other hand, additional contact spots occurs. So, but the average size is about the same all the time. And we also know that there is a linear relationship between the load and the real area of contact. We discussed that in the contact mechanics videos. And that means that the friction force is the real area of contact multiplied by the shear strength of the contact in the contact spots. So the shear strength here, we assume that there is a constant strength of you need to overcome a shear stress of tau to start sliding in that contact. And since the real area of contact is proportional to the normal load, it's a constant multiplied by n. That means that the mu is actually a constant multiplied by the shear strength of the interface here. And that shows you that the mu is simply the constant multiplied by the shear strength, and it's independent of the load then, as long as the shear strength is a constant, of course. There could happen things in the contact spots that changes this, so that makes the friction coefficient also to vary with load or speed, for example. Okay, let's start talking about the origin of friction. Why is there friction at all? So the first, maybe one of the most important, is the plastic deformation. So if you get plowing or indentation of the surfaces. So if you have a rough surface which is hard, you put it in contact with another surface and then you try to move it or slide it relative to the other surface. The rough hard surface may scratch the smoother and softer surface and plow the surface, and that is giving rise to dissipative forces, of course, or friction simply. That's one of the most important types of friction. The other one is adhesion. When two surfaces, two atoms on two surfaces come close to each other, they want to stick to each other, and you need some energy to overcome that contact. That's maybe the two most important ones. In a lubricated system, even if you have a lubricant film here, a fluid film in between the surfaces, then you don't have any plowing, you don't have any adhesion really, not very much at least. But then you have some viscous sharing of the lubricant film, and that is, even if it's a low friction, it's a frictional loss anyway. I'll discuss that more in the chapters about lubricated friction. Electrostatic effects could also occur if you have one surface charged in one way or another surface charged in a different way. They will create some attraction in between each other, and that may cause some friction. Normally in engineering applications it's not a big problem, so I will not bring it up at all here. But I will discuss the material hysteresis, which is due to viscoelastic losses. So as you may know, all materials are not perfectly elastic. Not even a metal is perfectly elastic, but in that case you may look upon them as perfectly elastic. But other materials like elastomers and rubbers, they are viscoelastic, and the visco part behaves like the lubricant I mentioned in the third bullet here. So you get a viscous loss in those materials, and that is very important for tire friction, for example. Coming back to that in later videos. Asperity interlocking is not seen as a cause of friction. You may think about that. You may, in your mind, when you stop the video, you may have been thinking like this: okay, it's the asperities on one surface getting stuck into the asperities of the other surface. And that has been a kind of discussion during the 1900s. So I think it ended in the 70s. That people saw asperity interlocking as an important origin of the friction. But nowadays we don't see that. Asperity interlocking falls into it comes into the plastic deformation and addition explanations of why there is friction. So we should forget about asperity interlocking. Okay, let's start with a plastic deformation type of friction, or we may call it also abrasive friction. That's because it's the type of friction you get when you grind, you take a sandpaper and grind a piece of wood. You know that there is a friction when you do that, and due to the abrasive action on the wood. So it's of course a dissipative process. It consumes some power, and the piece of wood and the sandpaper too becomes warm. Same when you rub your hands, by the way, a little bit the same. What is happening then? Well, there are a number of permanent changes of the surface topography going on there. So plastic deformation is involved in all of them. You squash the asperities, you dent the other surface with a hard surface, you plow the other surface by rubbing a hard asperity in contact with a softer counter surface. You may even cut away a tiny part of the material. And there is also something called shakedown, which is a part of the running in process where the microstructure is changed. And in all of these cases, maybe not in the shakedown case, the surface topography changes. So you have a kind of wear or running in of the surface, and that's due to plastic deformation. And all of those processes consume energy, power. So that means you have a friction. And the friction can be substantial, of course. So again, think about the example of walking on ice. If you have studded shoes with a very hard steel studs, then the steel is much harder than the ice. So you penetrate the ice and you get a good grip because you get a lot of plastic deformation of the ice. That also occurs when you walk with your studded shoes on your wood floor indoor, which you shouldn't, of course, but you have a good grip there too, but you damage the surface at the same time. You also damage the ice surface, of course. A simple plowing model is shown in this picture. Let's assume that we have a kind of a spherical asperity like this, and if this spherical asperity is sliding and it constantly deforming the surface, you create a resistance, a stress sigma multiplied by the area, the front area here, and at the same time you have some average area here in contact. You have the real area of contact multiplied by the pressure in the contact here, like which is normally the hardness, as you remember. And then you do some mathematics here. You can actually predict the mu in this case to some extent. The mu is the stress multiplied by the area in front of the asperity, divided by the pressure in the contact divided by the real area of contact. And since both the stress here and down the pressure here is equals the hardness, that means that the mu is actually the area in front of the asperity divided by the real area of contact. And with some mathematics here, we can find that it's actually an expression like this, where the alpha is a function of the penetration delta over the radius of the asperity. So if you plot this function with delta over r, you see that the bigger delta or the smaller r, the bigger the plowing friction coefficient. Before talking about how to reduce the friction, then we should also say that there is something called three-body friction too, and that is happening when you have a third body, a third material in between the surfaces, and that could be sand particles in between your shoe and the ice. It could be some other particles. So here it's again, it's important to think about the shape of the particles, because the shape of the particle, the size and the shape determines how much it penetrates into the other surfaces, and of course the hardness relative to the other two surfaces is important. So if you have again sand on ice and rubber shoes, the sand particles are harder than both the ice surface and the shoe sole surface, and that means that you get a good plowing friction in both interfaces. Okay, but how to reduce the friction then or the plastic deformation friction, I should say? Well, you can do that by reducing the delta over R ratio. You can, for example, do it like this, that you have a two very hard materials. That means that the delta will be small. You should also try to have the similar hardness of the two surfaces. That means that either of the surfaces can penetrate into the other one, and that also maintain a small delta. You may have a low roughness or a low roughness slope. In both cases you have a large R then. So instead of reducing the delta, you can also increase the R. And of course, if you want to reduce the friction, you should avoid hard irregular particles, contaminants, wear debris, or vice versa. If you want to increase the friction, you should use hard irregular particles like the sand. Okay, so that's the end of part one, and that was about abrasive plowing type of friction, and in part two I will discuss adhesive friction. Thank you very much.